Hello everyone, this video is to show you my presentations and the defense of my internship. You can see what I did in my internship and the optimizations part in this show video. This presentation is 15 minutes because of the limitation of the school requirement. Let's go started. Welcome to my internship defense. I'm very happy to have this opportunity to introduce my internship and the last in Toulouse. My internship topic is about object recognition and localization for the Talos humanoid robot. It will help in the future motion planning. In this presentation, I will mainly explain the problem I encountered in my internship with the results of each phase and the way to solve them. Before that, please allow me to introduce my internship unit and team. The full name of the lab is a Laboratory for Analysis and Architectures of Systems, which depending on CNRS, and the Jupyter team which I do my internship is belongs to the last robotic department. The research activity of the Jupyter team is to analyze and generate the movement of the anthropomorphic system. And my internship is based on the collaborative projects between last CNRS and Airbus, which called as Hope for Fun. During the internship, I used the leader on top of the hand of the humanoid robot to identify and locate objects for motion planning with the robot. The robot will use the information from the leader and the dataset of the target objects to identify the specified objects and approach it. The next slide will show a more detailed workflow. As we see, in my internship, I use a system to process 3D point cloud data, which is mainly used for scene and models to matching work by using FPFH descriptors. The input for the system is the scene information quantities by the leader, and the other is a multi-view model data set of the objects generated by the software gazebo. Then, the system uses PCR functions to vocalize the scenes and estimation FPFH and a series of the other processes. For the model, we use the K-mean algorithm to cluster them. Finally, the system used the two-input FPFH dataset to do the matching work and display the results based on the matching score and fit out the area where the target object is located. The goal of the internship at the beginning was to test the system, see if there was unstable results and optimize it. In the test, I got some unstable result. I like to show you a first result in the beginning. The yellow circle is the object we want to identify. On the left side, the point in each color represents the different matching score with the best part in green and the worst part in red. On the right side, the red color represents the no candidate area, and the blue color represents the candidate area. We can see that the green part with the highest correlations in the left graph belong to the blue area in the red graph. In the first result, we discovered that the objects in the scenes are not in the blue area. This means the target object is not the most related part. So we need to solve this problem. After the discussions, we think the problems might come from the clustering algorithm K-mean. The original number of the cluster was arbitrarily set to 100. So in the next test, we increase in interval of 10 until 100 to see the results change or not. We found that the results in 10 to 20s have been improved because there are more parts of the object covered with the blue area. 20 to 30s results from the change back to back. We suspect that was the source of the problems indeed in the K-mean algorithm. We have the two reasons for suspicion. One, the number of the clustering centers K need to be given in advance, but in practice, the selection of this K value is very difficult to estimate, and in many cases, it's not known in advance how many categories the given data set should be divided into be the most appropriate. The second reason is the different initial clustering centers might lead to completely different clustering result. when the initial clustering center of the k-mean is taken randomly. So we focus on optimizing the clustering k-mean algorithm within the system. Consult the bibliograph soon appears. I discovered the eligible method which is known for finding reasonable clustering of data. The specified step is, first, I use the sklearn k-mean, which is the machine learning library, to calculate the results of different numbers of clusters such as 1 to 100. And then I extract attribute obtained from each calculations, which is the sum of square distance of samples to their closed cluster center. Finally, I find a tool which named is kneat. It can detect the positions of the reasonable inflection point of the curve and return its value. This value will be added to the futures data index. There is a visualization of the eligible method on the right side. It shows a reasonable number of the cluster is the 16. After adding a reasonable number of the cluster indexed to the data, we found that the results be improved, but not enough. At this point, my supervisor proposed to try to pay-cluster the model's datasets of the first scale and observe the result. So I extract all FPFH data of the first scale and convert its reasonable number of clusters using the eligible method, and then use the middle k-mean plus to select the initial clustering center. And this time, it is no longer a random selection. Finally, we get a clustering result, the dataset we called all-in-one. After applying the all-in-one to the test, the results were further improved, and the target objects were correlated to be fully forward. We can see a clear change in the point color. However, in some scenes, the problem of different object poses lead to decrease in correlation. Like this example, some features of the front and back of the object are not being counted, so it's still not in the counted area. After we adjusted the ranking threshold setting from 10% to 50%, and this time the target object is kept in the counted area. In the upper part of this result, we can see that the result is still back if only the threshold is adjusted in 50% without using the all-in-one dataset. After ensuring that the target is in the counted area, we can start next searching to target the objects by reducing the scale and continue reducing the unrelated area. The distance between the target object and the robot in this test and the previous test was around 1.5 meters. Later, we also tested a long distance. This result here demonstrates that a distance of the 5 to 6 meters, our system can still lock onto the target object. During the internship, the most difficult part of the implemented test is finding the right tool to handle the data. As we can see in the Gantt chart, it took me about a month to analyze the results and find the right methods and tools to implement the next step of the testing. For example, some tools do not provide the parameters we need in their functions when it comes to identifying a reasonable number of clusters. Some tools have a restriction on the type of input data. Some tools need to be used in conjunction with another tools to get the result what we want. At the end, we are glad to see our system keep the object to be recognized in the counted area, and the object can be recognized in some far scenes. This facilitates the alignment work that follow. For the conclusions, a reasonable number's choice of clusters has a significant impact on the result, and some suitable methods can make the clustering algorithm more stable. The last step in the project will be the alignment work. where we need to find the most suitable view models in the results and the remaining scenes informations as inputs to the ECP alignment to obtain an estimate of the object's pose that will support the robot's motion planning. This is the part of my defense. If you want to know about more details, you can contact me. My contact details can be found on my personal website. Bye bye.